Welcome to this video recording of statistical modeling course offered by HEC Montréal. Today we're talking about the central limit theorem, which is perhaps one of the most important results of probability theory. And we will see why it's so important and how it ties up with the material we will be covering, and in particular, how we can use the central limit theorem to derive the null distribution of test statistics that are based on means, and also we will cover later maximum likelihood estimators. So if you watched the previous video where we were looking at hypothesis testing, one of the basic steps once we've chosen a test statistic, it's deriving its null distribution. What is the expected behavior? What's the benchmark that we need to compare our observed value to under the null? So if the null was true, what would we expect to see? What would be flagged out as being extreme or unlikely under the null? And that test statistic, so in the previous video, we were considering a one sample t-test, which is a scaled average. And oftentimes this test statistic will be a wall statistic. So either it's going to be a mean or it's going to be maximum likelihood estimator, and the central limit theorem would also apply to that particular case. Okay, and under regularity conditions, which I'm not going to dwell into, and provided that we have a big enough sample size, and we'll see how big that is, well, we can actually use a normal approximation for the null distribution. Why is it the case? Why does it work? Well, central limit theorem is the reason behind this magic. So here's an informal definition. Basically, we consider a sample of n observations from some population with a distribution which has a mean, an expectation of mu, and a variance which we assume is finite and is labeled sigma square. So what the central limit theorem tells us is that, well, the sampling distribution of the sample mean y bar n is approximately normal, is going to be centered at the expectation of the population, and its variance is going to be smaller than that of an individual observation. And how is it going to differ relative to that single observation? Well, it's going to be scaled by a factor n. Okay, so the variance of the mean is sigma square over n. So there's a lot of things going on in there. Let's go to the formal definition before we look a bit at some graphical illustrations to see what the theorem actually says. So more formally, if we have a sequence of independent and identically distributed random variables, so this is a bit stronger than that's what's necessary, I'll assume they have a common distribution f with finite variance. Y bar n is going to be here, I'm missing an inverse. Okay, so this is the sum of the y's divided by n, denote the sample mean. And then what the central limit theorem tells us is that basically the mean converges in distribution to a standard normal once suitably scaled. So you'll notice, so I'm talking about the probability of being less than or equal to y, and that holds pointwise for every y. And when you look at this square root of n times blah, 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 well, essentially all I've done is I've subtracted the mean, the expectation mu, and I've divided by the variance, which is by the square root of the variance, and the variance was sigma square over n. And so I'm dividing by sigma over square root of n, and the square root of n goes on top. So that's where the square root of n comes from. Okay, so if you scale at the proper rate, basically the sampling distribution is non-degenerate and it's normal. Okay, with mean 0 and variance 1. So let's see this in practice. I'm going to basically sample from an arbitrary distribution. So this is my distribution f, that's its density. So you can see the distribution is not normal. Actually, it's multimodal. There's a mode around perhaps 3. It's left truncated at 0, and the average kind of falls in between the modes, okay? And it extends into the tails up to about 40 or so, where then the probability becomes negligible. So what I'm going to do is I'm going to apply the theorem by basically looking at the distribution of the average from repeated sample. So I'm going to take here, you see 20 samples, okay, of size n equals 10. And for each sample, so that's in the dot plot, the red vertical line represents their sample average, okay? So notice how the sample average seems to be around 8, but oscillates quite widely, okay? In one of the outcomes at least, it's about 18. It goes to a bit less than 5. So this is when I draw 10 observations, and of course there's sample variability in there because I have very few observations in each sample. Let's repeat the same procedure, but now I'm going to just scale up the sample size. Right here are the same result with n equals 100. So you still see the mean moving around, but you see less of these extreme outcomes, okay? So the variability of the sample mean has decreased, and if I were to push the sample size up further, then it's, basically staying very close to 10. And you see also that the outcomes I get, if I was to do a density estimate, it would closely match that which I've observed, that which I drew for the data from. So what's going on here? So the central limit theorem tells us if you were to pick a particular red line, what is its expected behavior? So this is an histogram. So I've gone back to the 10 observation case, and I've drawn a histogram for 1,000 outcomes. So I've generated 1,000 samples. I've computed their sample mean. I've stored that, and now I'm showing you a histogram of where these sample means fall. So they go from about 3 to 20. They're centered around 10. And you can see a violet line which closely matches, but not completely. It's a bit off in the left tail. It seems that the distribution is a bit skewed to the left, okay, towards the first mode, but it's a pretty good fit. Now what happens if I scale up the sample size? Okay, here's the same picture, but now the sample's at size 100. And you'll see now with the blue line, sort of aqua, that the fit is actually a bit better. But notice the scale on the x-axis. I was going from 2 to 20, and now I'm going from about 7 to 13. So it's shrunk. It still looks like I have a bell curve, but the approximation's better in the tail. And actually, it's the histogram's a closer, the curve's a closer fit to the histogram. And if I power up with 1,000, so I'm showing you the 3 curves overlaid, one on top of another. So the yellow one is for n equals 1,000, and you can see, no, I'm barely within 1 unit of 10, which is more or less the sample mean and the true expectation of the distribution I was sampling from. So all of these curves are centered around 10. So they're all centered at the expectation, but as you increase the sample size, the variability of your sample estimate, because you're keeping more information, it makes sense that there's less variability because you're more certain about your estimator. And so from, say, the purple line to the yellow line, well, the variance is shrunk by a factor 10, okay, more or less, if you were to compute. And so this is the effect of the central limit theorem. It tells us 3 things. Your sample estimate will be on average, okay, an expectation, equal to the true expectation of your random variable. And that's how we derive a test. If you're trying to say, is the true expectation there? Well, you're going to use your postulated expectation, the parameter of interest, and you're just going to scale it up. And so if it's the correct value, well, your sample mean will be rescaled to 0. If it's not, then it's going to be shifted. And this is how we're going to find out whether it's shifted or not. So the first thing is its center at the right place. The second thing is the variance decreases at rate 1 over n. And so the standard error decreases at rate square root of n. And the third thing is, well, it behaves like a normal distribution for n sufficiently large. So for n equals 10, even here, the data did not look normal, right? Recall it's multimodal, it's left truncated. There's a bump and the average falls in the middle of the two modes. And yet, if you look at the sample average, they look pretty normally distributed. And so that's an effect of the central limit theorem. So normal distribution in large sample, and how large does n need to be? Well, it depends, but usually 30 is a good rule of thumb. If your distribution is more heavy-tailed, or lambda-kurdic, then perhaps a bit higher, so towards 30, but sometimes, well, for example, if that's normal, even n equals 1 is fine. But nature doesn't generate normal samples, yet because of the central limit theorem, the normal distribution is sort of the canonical distribution for test statistics, okay? So the variance, if you have an observation that has variance sigma square, so an individual observation can be anywhere, you know, if you looked at the density, it can fall anywhere. There's a lot of potential variability for this observation. But once you start aggregating, the sample mean has much less variability, okay? So information accumulates.